Hello, my name is Muriel Medard. I'm the Cecil H. Green Professor of Electrical Engineering and Computer Science at MIT. Today I'm speaking to you in my role as Chief Scientist and co-founder of Steinwurf. What does Steinwurf do? We work with companies like yours that have to deal with extreme environments and challenging settings for their networks. So what are the challenges? You guys know them better than we do. Ultra-reliable systems over systems that are inherently unreliable. And what do we mean by unreliable? They have very difficult physical settings, often extreme settings. They are liable to failure, but they always need to be up. They're heterogeneous, that is to say that you have a mix of Wi-Fi, of private LANs, of underwater networks, of acoustic networks, on pipes, that you have also satellite, and all of this is getting, of course, more complicated with a variety of IoT systems. These networks are also dynamic, which means that by their very nature, the state of them is very difficult to track and even, I would say, impossible to know with any real accuracy in real time. So anything that we do is going to have to be highly flexible no matter what the system is. So at a high level, what is it that we do? What we do is forward erasure correction, and I'll give you here a very simple view of how we operate, and then we'll go a little bit more in depth. So we start with the original packets, the data that you need to send, and we encode the data. What does that mean that we encode the data? We treat the packets, in effect, as very long numbers, and we create equations with those very long numbers. And these equations have to be done with enough richness, in effect, over enough choices of numbers, that they're likely to be independent of each other. As the equations, the packets, traverse an unreliable network, some of them are lost, some of them are corrupted, and the decoder at the other end recovers those equations, solves them in effect as a system of simultaneous equations to for whatever has been missed in the transmission, and is able then to reconstruct the original data reliably. All right, so surely people have thought of doing something like this before, and indeed they have. Traditional codes are block codes. And what I mean by block codes is that they start with all the data already known, and they were all developed for end-to-end systems. Mostly at the physical layer, that's to say very specific to the particular medium, be it satellite, be it twisted copper, be it Wi-Fi that you're working over, and some of them at higher transport layers like RAP2Q, but all of them knowing ahead of time everything needed to be coded and transmitted as though the entire network were just a single link. This is okay if you have a planned static environment where you don't have many hops, where in effect your network does look like a single link, or at least you only have control over a single link. But that's not what we see right now. What we see are the kinds of rich topologies, dynamic topologies that we mentioned before. And in that case, we need new codes. In particular, we need codes that can accommodate data as it comes. You don't know ahead of time all the data you're going to need, and you need to be able to provide it in a timely fashion. You also need the data to have delay guarantees, and by delay we mean in-order delivery delay. Having old information delivered may not count. You need to be able to know that the information is going to arrive in a fashion which is useful and actionable. So why they're new? They have the same advantage as traditional codes. They have low complexity, and we call them Rlnc, which I'll describe in a second what they are, random linear network codes. And we'll see how they're different from traditional codes. But basically, they allow for a completely on-the-fly operation, and they also allow for an operation that doesn't require to keep state. We are able to have, whether it's static or dynamic environments, and work optimally in all of these settings. So basically, we can match the performance, often outperform the traditional codes in static environments, but we're the only ones that can deal with rich, varying, non-point-to-point environments. Okay, and what is this Rlnc random network coding that I just mentioned? it is making the equations as I mentioned before, so that rather than taking the data, which has been segmented into packets, and which in order to be reconstituted needs the exact specific packets for reconstitution. So for instance, in this case, 2 green packets do not make up for the piece of the puzzle that's been missing here, the red piece of the puzzle. We do this construction of equations, but we do it using a random approach. And the randomness is very important because it provides the fluidity and the entirely on-the-fly approach that the other codes, which are all structured, all traditional codes are structured, simply cannot provide. So in this case, for instance, we see these 5 packets. We simply think of them as 5 numbers, and any 5 of those numbers will do. So for any k packets, any k mixtures will do. I'm showing the mixtures here as though they were sharded, as though they look like patchworks, but they're really equations. You should think of them as being degrees of freedom, new equations that are being constantly generated. And one of the great things, of course, about an equation is that if you take another equation and add the 2 together, or in some way mix them algebraically, you get another equation. And so you have an indefinite recoding capability without the need for intermediate coding. None of the other codes have that. How do we use our systems? Well, we have 2 main use cases right now: delay management, particularly in order delay management, which I've mentioned to you before, and also broadcast and unreliable networks. I'm going to cover a little bit more of this broadcast and unreliable networks, particularly when you don't have access to terminals, where you have many nodes that may need to have information updated, but you don't even know where those nodes are, how they're receiving, and what their capabilities might be. So in that case, here's our comparison with Rlnc and LDPC, so traditional codes, RaptorQ, which is a rateless code. Rateless simply means that it still starts with a block, but just keeps transmitting until everything was received, where the Reed-Solomon and low-density parity codes simply decide ahead of time how much they're going to send. And in these systems, what you see is that, our system has the best memory footprint, the best cache friendliness, which is extremely useful, particularly when you have unreliable systems which may need to pre-cache. We have very low computational complexity. We're highly parallelizable, and our reception overhead is extremely low. So we are also able, and this is of particular interest as updates and the amount of data that's being transported goes up, to deal with very large object sizes. This is directly a consequence of our parallelizability and our low overhead. In that context, let me just show you a bit of the future proofing that you get with our codes. I mentioned rich topologies. None of the traditional systems can deal with rich topologies, but we can. Let's take a quick look here. I have this mesh system with a source, a receiver, very, very high probabilities of loss, which I'm showing here. So we're looking at, losses of 70%, 30%, 80%. So we're trying to, in effect, communicate over a sheaf of very lossy systems, very lossy links. We allow here recoding at these blue nodes, and these epsilon 1, epsilon 2 are variables that we'll explore, the disparameterizations of even further losses. What I'm showing you here is the comparison between, on the left, throughput, and in the center, one measure of delay, and then the right-hand side, another measure of delay. These measures of delay correspond to average delay and maximum in-order delivery delay, so out-of-order delay, if you will. What you see is that on the left-hand side, of course, you want to be as high as possible. We are the blue. We're very, very close to the optimum on the throughput, and we're very, very low on average and in order delivery delay. Systems such as end-to-end codes, such as Raptor or any rateless, these are actually the codes we show here are better than those codes, but are not as good on the throughput, and some of them have very, very bad behavior with respect to delay. If instead you consider not end-to-end, but if instead you consider hop by hop, for instance, with something like repetition, which actually does require the kind of stateful operation that I mentioned before is of extreme difficulty in these sorts of systems. The hop by hop operation with ARQ, that is called repetition, is actually not as good as us, but at least it's on the throughput is getting a little bit more comparable, even though it requires a lot of state. But from the delay perspective, is extremely poor. It's even worse than system like the Raptor systems. So with that, I'd like to just leave you with some of your use cases. We have been working with several clients, such as Barracuda, very recently announced, for wide area network VPN optimization. We have been working with other clients with extreme systems, in particular such as EvoLogix for underwater communications. Many of you may be familiar with it. And also we've been working for connected cars, for the future connected car systems with the New York City Department of Transportation. And with that, we'll gladly take your questions.